Imagine sending a message from one side of the world to the other at nearly the speed of light, all through a strand of glass thinner than a human hair. That may sound like science fiction, but it's very real. It's fiber optics, the invisible backbone of our modern internet. These fragile-looking threads of glass carry over 95% of international data traffic, linking entire continents and powering the digital world we often take for granted. Without them, everything from global finance to streaming your favorite shows would crawl at a snail's pace. But here's the fascinating part. How does something so thin and delicate manage to transmit so much information so quickly across such massive distances? Today, let's unravel the incredible industrial process of how optical fibers are made. At the heart of fiber optics is a simple yet powerful idea: using light to carry information. Instead of electrical signals traveling through copper wires, fiber optics rely on pulses of light. These tiny flashes represent digital data in the form of ones and zeros. Lasers or specialized LEDs generate these pulses, which then shoot through the cable at speeds close to light itself. Crucially, the light is guided. A physics principle called total internal reflection keeps the pulses perfectly trapped inside the core, allowing them to bounce and zigzag for tens of kilometers without losing signal strength. To build this light highway, the manufacturing process is one of the most intricate industrial undertakings in the world, starting with the most basic ingredient: high-purity quartz sand. Only carefully selected deposits of white sand are suitable, as they must contain the high level of silica required for optical glass. The sand is extensively washed in industrial tanks using powerful streams of water and mechanical agitators to remove clay, fine dust, and organic debris. After the washing cycle is repeated, the sand is dried in industrial furnaces to remove all moisture. Instead of melting sand into a solid block, technicians convert the silica into gaseous compounds under high temperatures. These compounds react and condense into layers of ultra-pure glass inside a slowly rotating, hollow glass tube. As the glass is built up layer by layer, engineers carefully adjust the gas composition. This determines which section will become the inner core, the light path, and which section will form the surrounding cladding. The thickness and purity of each layer are tightly controlled, as even the slightest deviation can compromise light transmission. After many hours of continuous buildup, the glass tube solidifies into a dense, solid rod known as the preform. A typical preform is about 3 to 6 feet long and already contains the complete, scaled-up structure of the future fiber. The preform is moved into a towering steel structure, often rising over 60 feet tall. The top of the preform is held in place and fed into a special furnace, where the temperature can reach nearly 3,600 degrees Fahrenheit. As the glass softens, a small drop is pulled into a thin, continuous strand. The strand is drawn straight down to a diameter of only about 0.005 inch thinner than a human hair. Laser sensors along the tower continuously scan the fiber, measuring the diameter with high accuracy. This ensures the fiber remains perfectly uniform, from start to finish. From a single preform, the factory can produce optical fiber stretching for dozens of miles with consistent quality. The newly drawn glass immediately passes through a chamber filled with liquid polymer. This polymer is specially formulated to create multiple protective layers, an inner elastic layer to reduce cracking when the fiber bends, and a harder outer layer to resist impact and abrasion. The fiber then runs through an ultraviolet UV curing system, which instantly hardens the liquid polymer into a transparent, protective shell. The now protected fiber is continuously guided onto massive reels at the base of the tower. This high-speed winding process must maintain steady tension, as any excessive pulling or uneven winding can crack or deform the delicate glass. A single preform can produce continuous reels of fiber, ready for the next step. Multiple reels of fiber are arranged in parallel and gathered into bundles, ranging from a few dozen to several hundred strands. Manufacturers add reinforcing elements made of steel or Kevlar to increase mechanical strength. Kevlar is particularly valuable because it is lightweight yet many times stronger than steel in tension. The entire bundle is wrapped in multiple protective layers. An outer plastic sheath helps block moisture and provide insulation. Some cables also have a water-blocking gel pumped inside to prevent leakage and signal loss. For undersea cables, the construction is even more complex, featuring multiple layers of steel wires wound tightly around the bundle to withstand crushing deep sea pressure and resist damage from ship anchors or even shark bites. The cabling machine operates with precise rhythm, twisting the components evenly to maintain uniformity along miles of cable. Before any cable is deployed, it must undergo a battery of rigorous tests to ensure it can operate reliably for decades. Before any cable is deployed, it must undergo a battery of rigorous tests to ensure it can operate reliably for decades. The cable is stretched, bent, and twisted to check its strength. It's placed in thermal chambers that cycle from deep cold to extreme heat, or submerged in high-pressure tanks to simulate deep-sea conditions. The most critical step is full-length testing. Engineers connect both ends of the cable to optical transmitters and receivers, sending data, video, voice, and network traffic continuously for hours. The cable is only considered ready if the signal passes through the entire length without packet loss, distortion, or abnormal attenuation. Once the cable passes every test, the spool is loaded onto specialized cable-laying vessels. The task then shifts to carefully deploying the massive coils across the ocean floor. The ship must follow a pre-surveyed route slowly, often just a few miles per hour. In deep waters, the cable is simply laid on the seabed, but near shorelines, powerful plowing machines carve trenches to bury the cable, protecting it from damage. This effort began in earnest in 1988, when the TAT-8 line went into service, connecting America with the UK and France, and marking the true start of our era of global connectivity. From pure white sand to cables lying deep beneath the ocean floor, the journey of making fiber optics is a testament to human ingenuity. We've taken one of nature's most basic phenomena, light, and learned to trap it, guide it, and make it carry the lifeblood of modern civilization: information. The result is a vast highway of light that allows billions of people to communicate, learn, and enjoy entertainment with a single click. The next time your video loads instantly, or your call connects in seconds, you'll know that it isn't magic. It's light bouncing through a tiny glass thread, quietly working to keep the world connected.